Today we're going to be learning about the reason why the fundamental theorem of calculus works the way it does. You have already been exposed to the fundamental theorem of calculus. I showed you that shortcut when we were learning Riemann sums, so you could look at and compare your answers, but I never told you why it works. So that's what I want to focus on today with this example problem here. So I'm going to start by just reading the example I have here for you. It says, suppose a car is moving with a velocity in miles per hour, modeled by the equation v of t equals 3t plus 1 from t equals 1 to t equals 4 hours. The question is, how many miles, let me highlight over that, how many miles were traveled from t equals 1 to t equals 4 hours. So we're given a velocity equation, which is measured in miles per hour, and we're asked a different question about miles. Now, in Chapter 3, we were very used to going from position to velocity. We would just take a derivative. But now we're being asked to start from a place of velocity and go to position. So before I even start going through the rest of this, I actually want to show you this problem modeled on a graph. So what I did here is I graphed the linear velocity function here, 3t plus 1, and I did that from 1 to 4 hours. So you can see my time is on the x-axis in hours. My velocity is on the y-axis in miles per hour, and I'm graphing the equation 3t plus 1. So this guy right here is the velocity graph from 1 to 4. Okay, if I were to use, I don't know, let's say a left-hand approximation, a left-hand rectangle approximation from 1 to 4, it might look something like this. Like between 1 and 2, I would have my first base. I would pull up on the 1, come straight across, and down. And then from 2 to 3, I would come straight up on the 2, left side of the interval, cross and down. And then maybe one more rectangle with a delta x of 1, I'd pull up on the 3, come across and down. So if I were to add up the areas, sum up the areas of these 3 rectangles, I would have something. I don't know what I would have, but I would have something. So let's explore this a little bit further. So if I would just pull this rectangle, for example, let's look at the base. The base is 1 unit. Now that means, in this example, 1 hour. And the height right here, which is 4, is 4 miles per hour. So if I were to find that first area, the area of rectangle 1, I would multiply 1 hour times 4 miles per hour, and look at how those units work out. The hours would cancel, and I would just be left with 4 miles. Interesting. So it seems that area trapped under a velocity graph, the way the units work out, is giving me position. Okay? If I do area 2, the second rectangle, again, I have 1 hour, and my height here is, what am I at there, 7? Yep. So 1 hour times 7 miles per hour, again, those hours cancel, is going to give me 7 miles. And finally, area 3 is going to be another hour times this height right here, v of 3 would be 10. So 1 hour times 10 miles per hour is 10 miles. So if this car is traveling with this velocity during these hours, then overall, if I add these together, this car traveled 21 miles in that time frame. What I'm really trying to drive home here is this fact. I'm going to write it right here. The area trapped between a v of t graph and the t-axis is giving me position. Position in miles. The area trapped between a v of t graph and the t-axis is giving me position. Okay, so seeing that, I'm now going to go back to my worksheet here that we started with, and we're going to continue on. Okay, let's go to these bullets. Let's go back to our question. How many miles were traveled from 1 to 4? Now, we now know the answer is 21. Well, not the exact answer. We know that the underestimate is 21 miles, but let's just go here. This question is essentially asking us to move from velocity to position. Second bullet, to move from position to velocity, we simply take a derivative. This was chapter 3. So, it seems reasonable that to move from velocity to position, we simply take an, I hope you're thinking, antiderivative. And this is some new terminology coming at you. We've been using the word antiderivative throughout the chapter. There is another synonym for antiderivative. So antiderivative is also known as indefinite integral. So you just need to know that if I say indefinite integral, it means the same as antiderivative. Okay, so we're going to take an antiderivative like we learned in the very beginning of chapter 5. So here we go. So if I'm taking the antiderivative or the indefinite integral of velocity, 3t plus 1, okay, that is my v of t equation. This is measured in miles per hour. And we do this with respect to time. This is like my delta t, which is measured in hours. You can see how when I multiply miles per hour times hours, the end result is going to be miles. So let's go ahead and anti-differentiate. So we know that to anti-differentiate, we add 1 to the exponent. So right now t is being raised to the first power, so I know t will go to the second power. And then I'll take my coefficient 3 and divide it by this new exponent. So 3/2 t squared plus the antiderivative of the constant 1 with respect to time is just going to be t, because the derivative of t is 1. And then I add that arbitrary constant c to the back. And I just know that this is going to be measured in miles because of the way these hours drop out. Okay, moving on. Now it says there is also something called a definite integral. So we went from indefinite to definite. A definite integral has a lower and upper limit of integration. So watch how we change from here to here. All I added in here was a lower limit and an upper limit on my integration. So from 1 to 4, and that equates from up here 1 to 4 hours. Okay, so we want to know how many miles we're traveling specifically from 1 to 4 hours. So let's do the integration again, and let's use the fundamental theorem the way I showed you last week. So we already know the antiderivative from up top. It's 3/2 t squared plus t plus c. We know to put our bracket here and to bring along the lower and upper limit of integration. And again, this is miles. Okay, now when I taught you this last week, I told you to take the upper limit and plug it in here. So let's go ahead and do that. So let's take 3/2 times 4 squared plus 4 plus c. Now that is going to be a certain number of miles. And I actually want to go to my next graph here to show you what that represents. So basically, if this is going to give me my miles traveled, and I plug a 4 into it, what that is essentially giving me, guys, is this. Here's that same graph, 3t plus 1, okay? If I plug 4 into that, it's actually giving me all of the area trapped from 0 to 4. So it's giving me, I'm going to lightly shade this, all of this. By plugging a 4 in, you're assuming that you're going from 0 to 4. So this will be all the miles between 0 and 4 hours. Now, I don't want all of that. I want a little less than that. So I'm going to subtract the value of the antiderivative with a 1 plugged in. So that is going to give me 3/2 times 1 squared plus 1 plus c. This is also a certain number of miles. Well, which miles? Well, let's look back at our graph. If I plug a 1 into the antiderivative, then that is assuming to take the total miles traveled from 0 to 1. So if I take 0 to 1, this area here in red, I'm taking this away. I'm subtracting it. So I take all that pink and subtract this red, and that should give me the area trapped between 1 and 4, which is exactly what I want. So hopefully that makes sense. So that's why in the fundamental theorem of calculus, you subtract these two. And then you just continue on. So let's just say this is miles traveled from 0 to 4 hours minus the miles traveled from 0 to 1 hours, and that is going to give me, let's see here, 3/2 times 4 squared is 24 plus 4 plus c minus 3 over 2 plus 1 plus c. And if you calculate this, you're going to get 25.5 miles traveled between 1 and 4 hours. And if you notice, the C's drop out. And in fact, the C's are always going to drop out because of this subtraction. So you'll see as we go along further into the chapter, when we're doing definite integration with boundaries, we're going to actually start discarding that C because it's kind of pointless to bring it along. It's always going to fade out in the subtraction portion of the problem. And just so you can see here, 25.5 miles makes sense because if you remember, our underestimate was 21 miles, and we did have a lot of error here. So that makes up for that, so 25.5 miles. Thanks for watching.